on the same page and sharing information so that we've got good science going into better decision making on all sides of our site work. Not getting my slide to advance. There it goes. So what ITRC does is they select projects that are identified from their membership or suggested through state agencies in particular. But in fact, for the PFAS team, the initial impulse came from some consulting firms who were frustrated that state agency staff they were trying to work with weren't really getting what the PFAS thing was all about. And so trying to bring everyone up to speed quickly on this rapidly evolving system or issue. So they form a team. That team then brings together experts from all of the different sectors. So industry, consulting, state, federal, and local government, stakeholder organizations, academia, to try and broadly share the information that's available on a particular subject, and then develop materials that are focused primarily at technical staff who may be too busy to dig into the vast scientific literature, but need to have that information distilled so they can make good decisions. We also do a lot of outreach and training, and then hopefully that helps to implement solutions. The ITRC team began in 2017. We currently have over 400 PFAS experts from all those sectors that I mentioned. In 2017 to 2018, we produced a series of fact sheets. Now, these are not your normal fact sheets. They're about 10 to 15 pages long. They look at different aspects of PFAS knowledge and provide fairly extensive reference lists. But the goal was to distill that information down and then provide you with the key references so that you could get up to speed on different aspects of PFAS quickly. Since then, we have been working on developing what we call a technical and regulatory guidance document. It's a more in-depth, more detailed document that covers more information about the areas covered by the fact sheets, but we've also added some additional areas like risk communication, including a risk communication toolbox that we're developing, stakeholder perspectives, and a lot more on toxicology and both eco and human health risk information. We've developed a one-day training workshop that we are currently holding, trying to have one in each of the EPA regions around the country. We'll be conducting those through June. You can see those on our website. And then we will also be developing internet-based training, and you can register for our trainings at this web page that you see on the screen. The fact sheets that we developed, as I mentioned, we published them over the course of 2017 and 2018, delved into 6 major areas of information about PFAS, including their history and use, their naming conventions and physical and chemical properties, their regulations, guidance, and advisories that are out there, environmental fate and transport, site characterization tools, sampling techniques and laboratory analytical methods, and remediation technologies and methods. And then in October last year, we also produced a fact sheet around AFFF. It was slightly different in that it focuses a little bit more on people who are using and managing AFFF at their site. So it gets into some best management practice recommendations. These, as I mentioned, are tailored to the needs primarily of state regulatory program staff, but they're useful for anybody who in a technical capacity or a project management capacity who wants to learn more about the issues. And you can see these are available online. They've got extensive and current references. I'm gonna just go back a second. And we recognize this is a rapidly evolving area of information. So when critically necessary, we do go back and update some of the fact sheets. More importantly, we have some regularly updated data tables that I'll talk about in a minute. As I mentioned, there's useful and usable content in these fact sheets, such as the historical information. This gives is an example of one of our figures showing the timeline of different PFAS, when they were introduced, what they've been used for, when they've been phased out. There's an assessment of the problem, the scope of it, and where we're at currently. The fate and transport and the history and use fact sheets contain some site conceptual models that give you a sense of where are the places we need to be looking for PFAS if we have a release at our site. Some of them are not entirely intuitively obvious because these things are so persistent, so soluble, so mobile. They travel to places we typically don't look for when we're dealing with persistent organic contaminants. And I mentioned we have updatable tables. So 2 of those include treatment technologies. Our team working on treatment technologies are continuing to update these tables as technologies are developed, pilot or bench scale tested, or then proven out on actual site applications. So this is a useful and regularly updated table that you may find. Possibly even more important to everyone out there trying to work across different states is our regulatory and guidance values spreadsheet, where we not only try to track all the drinking water, groundwater, and other guidance values, including some soil and sediment values. We are updating this roughly every 2 months because this is such a rapidly evolving situation out in the states. But we also provide background information on how some of these were derived, what the key studies were that were used, and whether or not they are promulgated and enforceable standards or guidance values and what have you. So this is one that you can go back to regularly to check on the status of different states and what they're doing. We do also include a few international standards and guidance values in these tables. So to give you a quick overview of PFAS regulations and guidance, this is a figure from the history and use fact sheet that gives you sort of a general sense of the iceberg of PFAS that we're dealing with. People throw around numbers of 3, 4, 6,000 of these chemicals having been synthesized at some point, whether or not they're actually out in the environment, whether or not they're of environmental or human health concern is still largely unknown. We are still at the tip of the iceberg. And so you can see from this diagram, the early attention was focused on PFOS and PFOA, and that's where those are where we have federal values and not even enforceable values, as I'm sure most of you are aware. Attention has quickly shifted, though, down this pyramid to the other perfluoroalkyl acids, such as PFHXS, PFNA, and some of the long chain PFAS that we're picking up in people's blood in the national studies and global studies that have been done. In addition, other chemicals are on the list of state values because what they find in their target analyte list that's showing up in their drinking water, states are trying to set toxicity values or health-based values for those chemicals. And so we're in a situation where we have different lists in different states and different values being set based on how they derive their health-based values. On top of that, we've got analyte lists that incorporate pretty much the full list of perfluoroalkyl acids, or at least the ones from about 4 carbons up to either 12, 14, or 20 carbons, depending on the contract lab that you're using. But the labs have gotten very good now at analyzing for the perfluoroalkyl sulfonates and carboxylates. And so that's what is really driving which chemicals have guidance values. It's what we're testing for, and then what we're finding, and then what do we tell our users, the citizens of our states, about those chemicals. Meanwhile, our friends at the analytical labs are continuing the work they do so well and giving us additional analytical capabilities that are finding some of the precursor compounds, such as the fluorotelmer compounds, the perfluoroethers, and the perfluoropolyethers, and including things like GenX, and which is a dimer acid, and the compound Adana, which are starting to be found in some states where they're looking for them. So we're in a period of great flux, and most of the toxicity numbers or the health-based values are being driven by what we're looking for, and that's going to continue to roll out as a slow creeping public health concern crisis, if not an actual health crisis, over the next several years. Regulatory approaches have been sort of all over the map. EPA did issue provisional short-term health advisories for PFOS and PFOA back in 2009. Those were replaced in 2016 by the lifetime health advisories of 70 nanograms per liter, so parts per trillion for PFOS and PFOA. Either individually or combined. Again, those are not enforceable, and so many states have adopted those values, but there are 6 states that have drinking water values that differ from EPA's lifetime health advisories, and 9 are different from EPA's drinking water health advisory levels. 19 states have some kind of criteria in water. States are also taking a variety of approaches for other PFAS. 6 states have criteria for some of those other compounds, the perfluoroalkyl acids. North Carolina has a number for GenX. Texas is kicking everybody's butt. They've done numbers for 14 PFAS in addition to PFOA and PFAS. So we've got a lot of variability, as this next figure illustrates. These are the PFOS and PFOA values that are being used across the country, and also a comparison to what Australia and Canada are using. And you can see they took exactly opposite approaches, with a higher value for PFOA and a lower value for PFOS in Australia, and Canada's got just the opposite. So there's a lot of variability and a lot of confusion on the part of the public. And of course, anyone in a state that's got higher values is under a tremendous amount of pressure, because the public gets online, sees these lower values being published by other states, and has a lot of questions about why are you not protecting us the way those other states are protecting their people. So it's a very difficult position for all of us right now. States that have values for other PFAS are shown here on this map, and 4 states are also doing some form of an additivity calculation for additional PFAS. Vermont, Massachusetts, and Alaska do a direct summing of 5 PFAS. Their lists are pretty similar, but their limits are different. And then Minnesota uses a TEQ-like process for the 5 PFAS that we have guidance values for. So it's a slightly different thing to weight each one based on their toxicity, their relative toxicity. And this is just another illustration. This is for soil screening and guidance values. You can see there are a number of states that have set some values for soil, and the numbers vary quite broadly depending on what the goal is. So the upper higher values are to be protective of human health through direct contact with the soil. So because there's very little transmission across the skin, little absorption through that route, these numbers tend to be higher. But when we're trying to protect against leaching to groundwater or drinking water, those numbers drop off dramatically. And so very restrictive numbers for that sort of protection level. Some other things that are driving regulations both at the federal and the state level is the absence of enforceable standards for any of the PFAS, even though we have some drinking water guidance. Another critical problem is PFAS are not yet recognized under CERCLA as hazardous substances. So there's no cost recovery for Superfund sites. They are considered a pollutant or contaminant and can be investigated. There have been some cleanup actions taken, but it's putting federal agencies, as I'm sure you know, and even states in a tough position to mandate or enforce cleanup actions at Superfund sites across the country because they are not yet considered a hazardous substance. And a bill was just dropped in Congress to declare them a hazardous substance, and we'll see where that's going to go in the current political climate. Other things that are happening, site investigations and their management are being driven by a lot of other forces, including voluntary action programs. Often these are being driven not only by regulatory, but public perception pressure. And this is a real issue because there is not much distinction on the part of the public between the different PFAS and how they behave. There's little understanding of how they behave in the environment. And this may be forcing actions that may not be necessary. We're still trying to figure some of that out, but that is driving an awful lot of decisions. Litigation, the Clean Water Act TMDLs are also being used to drive site investigations and management. And then there are a lot of approaches going on at the state level. So it's really critical that you consult your local regulatory agencies and your legal counsel when you're trying to figure out what's going on in the particular state or locality where you're working and what actions you're going to need to undertake. There's also an evolving problem with disposal regulations. We were just having a discussion about that this morning, the fact that some landfills are starting to require testing for PFOA, PFOS, or a suite of PFAS and refusing samples that contain them, which, given the potential for airborne deposition and non-point sources, is a real concern. Wastewater treatment plants are starting to make sounds, or in some places have refused leachate from landfills or investigation-derived waters. So it's starting to become a problem because a lot of people are starting to look at their potential liability if they accept PFAS-contaminated materials. And I'm going to leave it at that because we got a lot of exciting speakers coming up. I understand we're going to hold questions until the end, and so I'm going to turn the controls over to Kavitha Dasu, who's going to give us a really good talk about forensics and fingerprinting.
Okay, thank you, Jenny. As Jenny mentioned, if anyone would like to submit questions, please do so via the chat feature, and we can address those after all the presentations have been completed. Our next speaker, Dr. Kavitha Dasu, is a principal research scientist at Battelle. Dr. Dasu has over 7 years of experience in studying the fate of emerging organic contaminants, such as PFAS and other emerging contaminants in complex environmental matrices. At Battelle, Dr. Dasu has been providing subject matter expertise in areas of developing novel analytical methods for total PFAS, fate and transport assessment, and development of remediation technologies for PFAS. Dr. Dasu has published several peer-reviewed studies and book chapter on PFAS analytical methods, fate and biodegradability, and serves as a peer reviewer for scientific journals. Dr. Dasu holds a PhD in environmental chemistry from Purdue, a Master of Science in Organic Chemistry, and a Bachelor in Science in Chemistry from Osmania University in India. I'd now like to turn it over to Dr. Dasu to present a PFAS fingerprinting approach.
Thank you, Michael, and good afternoon, everyone. Today, I'm unable to move the slides. Yeah, I got it. Sorry about that. So today I'll be talking about the per and polyfluoroalkyl substances fingerprinting approach. To understand the fingerprinting of these chemicals, and knowledge about the PFAS chemistry, sources, and history of use is very important So I will be providing a brief background on the PFAS sources, followed by a small study which we have done in-house for the to understand this fingerprinting approach will be presented, followed by results and the conclusions from that study. So Ginny actually has laid out a really good timeline of the manufacturing of these chemicals and their applications. I'll just slightly go over these things. These are mainly used for as a surface coating for the imparting stain resistant and oil resistant properties on the commercial products, and they're also used as a performance chemicals for industrial applications and also AFFF. So looking at the manufacturing processes, this is very important information when we are trying to understand the fingerprint of these chemicals. So there are mainly two manufacturing processes are used for producing these chemicals. One is the telomerization, where by using these processes, they produce the polymer products are produced, which are mainly linear even chain length chemicals, and those are polyfluorinated chemicals. The other manufacturing process is the electrochemical fluorination, which is mostly sulfonates are produced using this process, and it results in a mixture of even and the odd chain chemicals. And that could have a mix of around 30 to 40% of branched isomers in that. And again, the main timeline which actually dictated some of the chemistry is in 2002. Until then, there was a more of a electrochemical products were out there in the market, has phased out the longer chain PFAS related chemicals. And after that, around EPA initiated a PFAS stewardship program. According to that, by 2015, all the major manufacturers agreed to stop producing the longer chain PFAS chemicals. So this action actually resulted in producing some of the shift towards the shorter chain length chemicals and their alternatives. So this information will be helpful in understanding what type of chain lengths or the chemistry we are seeing in the products and how we could relate to different sources of these chemicals. And looking at some of the sources of the PFAS, we could broadly categorize them as some of the direct sources and also the indirect sources. Direct sources, the industrial sources, mainly the manufacturing plants and some of the textile and the plastic coating plants and the metal plating facilities could be considered as the direct sources, and others are the AFFF usage for many like fire training areas, airports, oil refineries, etc. And the indirect sources could be from the landfills or the wastewater treatment plants, which are not actually equipped to treat some of these chemicals. So whatever goes in might also come out, but more to that is some of the biodegradation which happens within these facilities and produce some of the precursors undergo biotransformation to produce some of these PFAS chemicals. And so we can see some of that fingerprint also from the sources of landfills and the wastewater treatment plants. So the fluorotelomere-based AFFF could also be considered as the indirect sources because they also break down to produce some of these final degradation products. So the fingerprinting, what is the fingerprinting? How we are going to use is, this is the environmental forensic technique, which is more commonly used for tracking the sources of chemicals with distinct chemical signatures. And this is more commonly used for the legacy contaminants such as PCBs, PAHs, and also some of the petroleum hydrocarbons. So, and to having this information in hand, will help us understand the fate and transport of these chemicals, some of the source tracking which we could do, and also understanding the concentration and the composition of chemicals. We can link those things to the contamination source scenarios. This all can be done by identifying the source contamination based on the chemical signatures, manufacturing, their chemistry, fate and transport data, and also the degradation pathways, as I explained earlier. although there are more commonly detected chemicals are seen as a background in each and every single source of these, for these, in this class of chemicals, there are distinct signatures of these chemicals based on their applications or commercial uses of these things. Some of them are for paper and the food packaging, phosphonic acid related PFAS are more commonly seen. So that could be considered as a signature chemistry for the paper and food packaging industry, and some of the metal plating as such, and also for the plant protection agent, it is also the ethyl foci is more commonly used. And when it comes to textile and leather industry contamination, these are the more of fluorotelomere polymers, and the most commonly used of polymers and their raw materials are related to the fluorotelomere, acrylates, methacrylates, and so on. Looking at the signature of AFFF related chemicals, this is a very complex chemistry which is there in the AFFF, which includes the anions, cations, zwitterions, and also the neutral molecules. But most chemical which is seen at higher concentrations is the PFAS and its related chemicals. But there are other fluorotelomers are also present in these AFFF related materials as betanes and amino oxides. The other thing would be the wastewater treatment plants and landfill leachates. As I mentioned earlier, the presence of some of the biodegradation end products such as fluorotelomere acids, N3 and N2 unsaturated acids would be a clear sign of biodegradation happening at that source from the fluorotelomere products. The isomer profiles, looking at the isomer profiles will also link the contamination back to the sources of electrochemical fluorination chemistry. So that will be very important to know. And the concentrations of some of the higher levels of odd and even chain length chemicals. So that will also link to the electrochemical fluorination manufacturing process. Apart from all these signatures and everything, environmental fractionation, fate and transport data is very important because these chemicals behave differently under different environmental conditions. Like suppose if there is a source like groundwater and the soil, how they partition into these matrices will also determine in making some of these distinctions. So going forward with all this background information, we designed a study to understand this fingerprinting approach. So the main goal was to determine the concentration and the composition profiles for these chemicals from different contamination sources, and to identify the sources based on the chemical signature, manufacturing, age of the release, fate and transport, and the degradation products. Going to our study. So this is our workflow, basic workflow for the study, where we collected samples from different distinct sources, which we thought would have some signature in that, and followed by the processing of samples and analyzing these samples using some of the targeted analysis where we have the known standards available, and we could quantitate the concentrations of these chemicals using the LC triple quad. And also in parallel, we also did the high resolution chemical analysis. This high resolution chemical analysis was done for chemicals, for all the chemicals actually, even for the chemicals having the standards and which doesn't have any standards available. We are doing a non-targeted analysis using the LC-QTOF instrument. Once after collecting all this data processing was done, a lot of data filtering was done because the high resolution chemical analysis data, we generate a lot of data, almost around a terabyte of data was generated from this high resolution mass spec. And using all this data, we have actually developed a library of PFAS related analytes and categorize them under distinct sources of these chemicals based on their fingerprint. Followed using all this information, we have done for the confirmation of our results, we have also done some of the statistical analysis. So the samples which were collected were from the environmental samples, surface water, which was collected nearby an airport, which was known to have a fire accident was happened nearby this source. So we went ahead and to collect some of the surface water samples nearby a metal plating facility, textile mill, which is known to use the fluorotelomere coatings, and also a wastewater treatment plant effluent and the landfill leachate. A carpet was also, we also extracted a carpet which was before a 2002 phase out, and also the AFFF formulations itself, because we don't know what could be the chemistry of the, we need to know the source of chemistry of the source. So we also went to look for the known AFFF chemistry. So we had one fluorotelomere based AFFF, one electrochemical based AFFF, and 2 unknown sources. So the extraction followed the common method, which is used, the method which is compliant with actually the DoD QSM 5.1 method was used for the extraction, which is done basically by the SPE extraction, followed by the LC-MS-MS analysis. The samples were also analyzed in parallel for the non-targeted analysis on the LC-Q-TOF. The branched isomers, having the information of the branched isomers will be useful to if there is an electrochemical manufacturing source which is involved. So we also quantified using a branched isomer standard. So this is a fingerprint of the environmental samples which we generated from the targeted analysis, where we quantitated the concentrations of these known chemicals. On the x-axis, we see all the analytes, carboxylic acid, sulfonates, and also some of the precursors, FOSAs and the FDSs. On the y-axis is the concentration of these chemicals in nanogram per liter. So the bars, blue is the airport here, sample, landfill leachate, and the metal plating. All the analytes which were detected are shown here. As we can see, the landfill leachate has a very high concentrations compared to other environmental samples. And the presence of some of the precursors in landfill leachates and nearby airport tells that these are both precursors and also the intermediates of some of the other precursors. So that tells the degradation products are also seen in these samples. So to look for, this is the data generated from the non-targeted analysis. So for this data, we have that was a huge data. So we went ahead to do the statistical analysis using the principal component analysis. So this is a statistics tool which allows the visualization and analysis of the data more than just a simple XY axis 2D plot. So here I'm using the data input for the from the high resolution mass spec data of all the samples. Mostly the PCA reveals the clusters of mass spectral data associated with each sample. So when we are having the unknown samples which are overlaid on this data, it shows a degree of similarity between both the samples, known and the unknown, or if there is any comparison between the unknown samples. So using this data, we compared the samples from the airport, which were around 6 samples were there, and the landfill leachate and the metal plating. And denotes the number of samples. This was a very small study as a proof of concept. So the vertical axis in the middle shows has a distinction between left and the right portions of the plot. And the landfill leachates falling completely towards the right portion shows that they are distinctly different from the other environmental samples. And at the same time, even the airport samples, although airport samples and the metal plating facility samples were on the same component, they are again divided into another horizontal axis, showing some distinction between the airport samples and the metal plating samples. So this was very interesting to know that statistics we have the confirmation from the PCA analysis, the distinction among different sources. This is a fingerprint of AFFF samples, and from the targeted analysis, what we got. The yellow bar shows the fluorotelomere-based AFFF. Green bar shows the unknown AFFF, and the light blue bar shows the unknown AFFF. Whereas the ECF, electrochemical fluorination, shows the dark blue bar here. So the concentrations of the electrochemical fluorination AFFF are very high concentrations were found, especially the sulfonates. The PFAS concentration was around 1000 ppm in this. Whereas all the unknown AFFF JZ33, which is a light blue bar, has a similar fingerprint of the AFFF samples, but the concentrations were a little different. When looking at the fluorotelomere-based AFFF, which is the yellow bar, was showing some of the precursors present in that. And so as the unknown AFFF JZ34 was also showing some of the fluorotelomere-based precursors in that. That shows that unknown AFFF might have some of the unknown fluorotelomere-based chemistry in that. So this is the high-resolution mass spec data for the fluorotelomere-based AFFF. Here down the x-axis is the retention time, and the y-axis is the M/Z values obtained from the instrument, and the bar size of the circles denotes the response for each of the specific fragments. And overlaying the ACF-based AFFF, although we have some commonalities in between, both show distinct features which are different from each other. The fluorotelomere-based are the green, and the gray ones are the ECF. So now overlaying the unknown AFFF on the same plot, we see some resemblance here, having it is so much similar to the fluorotelomere-based AFFF. That is so similar that we could say the signature of this unknown AFFF is similar to the fluorotelomere-based AFFF. So this is actually really cool data. So this data is very important to identify some of the co-occurrences of these AFFF chemicals. This information also provides some insight into the time period of release of these chemicals, especially if there is at a contaminated sites where different AFFFs were used over time. Having this information, we can identify specific signatures that could be used to actually date up, understand the date of the plume. So further analysis of what could be these chemicals are chemically, we have seen based on their M/Z values, they were the fluorotelomere sulfonamidobetanes, which were seen there from the unknown and the fluorotelomere-based. And further, the PCA analysis, as I explained earlier, the statistical analysis has shown that the fluorotelomere-based AFFF and the unknown AFFF, which was similar to the fluorotelomere-based, were clustered separately compared to the other two AFFF, which is the ECF-based and the other unknown AFFF. So this clearly tells that we can identify some of the different sources, if not, so we can identify different sources, but again, at the same time, the unknown AFFF, which was also showing similar signature of the ECF, was different in the principal component analysis. So that could be maybe the formulation of this AFFF might be different. It might also be the same ECF, but the formulation might be different. So that could be the date of that AFFF might be different from the other ECF-based AFFF. So further analysis of the detailed analysis of the fluorotelomere-based AFFF, we have seen some of the precursors which are known which are reported in the literature. All the M/Z values are the precursor ion M/Z values. And interestingly, we also found the 14,2-betaine was also found in this particular AFFF, which was not reported in the literature, but we have seen in this current study. And the sulfonamidoamines were also detected in the same samples of the fluorotelomere-based AFFF. That clearly tells that the source of this AFFF and the unknown AFFF was fluorotelomere-based AFFF. The ECF-based AFFF has shown mix of many perfluorinated alkyl acids and linear and both branched isomers were also seen in the ECF-based AFFF. With all this information, what we collected, we are able to identify fingerprints of different AFFFs. So in conclusion, we collected some of the PFAS fingerprints from various environmental samples, and we created a library, spectral library of it. And some of the key factors to consider when comparing these distinct source signatures are the manufacturing source, the timeline of release, which will be very important, and the fate and transport and the degradation products. Further identification and the confirmation of the analytes and the statistical analysis of the data is still in progress, so more to come. And my sincere acknowledgements to all the Bathel team who helped in this research. Thank you for your attention, and for more information, you can visit bathel.org/PFAS. Thanks, everyone. And with this,
okay, thank you, Kavitha.
Yeah.
I'd now like to introduce our third speaker. Dr. Andy Martin is a supervisor environmental L at U.S. Army ERDC EL in Vicksburg, Mississippi. He received a Bachelor of Science in Chemical Engineering from Purdue University, a Master of Science in Civil Engineering and Environmental Engineering from the University of Illinois, and a Doctorate of Philosophy and Ecological Sciences and Engineering from Purdue University. Dr. Martin's current research is related to emerging contaminants and materials in the environment, such as insensitive munitions and PFAS. He is on the internal ERDC PFAS working group, aligning public-private partners to solve research problems. Dr. Martin is a collaborator partner with GSI on the SERDP project ER 18-1839, investigating the PFAS air-water interfaces within the Veda zone, and his group is involved in other PFAS fate and transport research. I'd now like to turn it over to Dr. Martin to present leveraging strengths to address PFAS environmental challenges. And Andy, you would have to unmute yourself when you start.
Andy, you're a third person down if you'd like to unmute your line. I'm going to have to unmute everybody, so please can you make sure that your own devices are unmuted? Unmuted, thank you.
This is great. As the title says, my talk is about how the Engineering Research and Development Center, or ERDC, is leveraging our strengths and the strength of our public and private partners to address PFAS environmental challenges. Next slide. Can you hear me?
Yes, we can hear you, Andy.
Okay, next slide, please.
You're on the agenda, the next slide.
Okay. I think there's some, that's fine. There might be some interference with my computer right now. Here the agenda is the focus of my talk, where I'll talk about the ERDC's approach to PFAS through our analytical, fate and transport, toxicity, and remediation efforts. Next slide. For those of you who are not familiar with the U.S. Army Engineer and Development Center, or ERDC as it's commonly known, it is a research lab for the U.S. Army Corps of Engineers and also the U.S. Army. ERDC has 7 labs located in 4 different locations identified as the yellow stars on the map, primarily in Champaign, Illinois, Vicksburg, Mississippi, Alexandria, Virginia, and Hanover, New Hampshire. We also have multiple field offices located around the United States and 1 in London, England. I sit in the Environmental Lab in Vicksburg, Mississippi. Next slide, please. ERDC currently has 6 business areas where we do research, ranging from civil works and water resources, supporting the navigation channels for the Corps of Engineers, to military engineering, supporting the warfighter, to environmental research and development. ERDC has developed a strong R&D portfolio related to analytical development of military unique components such as energetics, like RDX and TNT, heavy metals such as depleted uranium, tungsten, and lead, physical and numerical model development for contaminant transport and flood, and also flood events for the nation. We also do a lot of work related to environmental toxicology of contaminants and the remediation of such platforms such as sediments, soil, water, and wastewater. Next slide, please. So the ERDC, through our efforts of engineers and scientists, have developed a PFAS working group to develop an enterprise-wide strategy for the Corps of Engineers in assistance with our district offices to address the growing concern over PFAS contamination. The ERDC working group is positioned to leverage our technical resources and leadership expertise in assessing contamination, risk analysis, and providing management solutions while partnering with public and private sector to leverage our collective resources. I kind of emphasize here partnering with public and private sector. The ERDC knows that we have capabilities, but we also know that there are other capabilities out there that are much further along than we are, and we want to leverage those and learn from those to make a better solution to solving PFAS. Specifically, the ERDC PFAS working group has identified 4 areas where we can best leverage our expertise and leadership as listed here. We've gone through an extensive SWOT analysis and came up with these 4 different criteria, one being analytical capabilities, the second being fate and transport, utilizing our modeling expertise and models that we've developed over the years, toxicity pathways and their understanding in the environment, and also our remediation and the development of best management practices, or BMPs, to deal with such contaminants. Next slide. So analytical, ERDC has cut our teeth working with private sector companies and universities, learning how to analytically identify and quantify some of the toughest military unique compounds such as RDX, TNT, tungsten, depleted uranium in the environment, from developing extraction and detection methods to using the full suite of analytical instruments and compound signatures on such instruments as the HPLC, UV-Vis, and mass spectrometry detection capabilities. Recently, our focus has shifted from traditional energetic compounds to such compounds as insensitive munitions and the suite of PFAS compounds. By using our technical expertise, we're able to leverage the work that we've done in the past and develop new technologies and enable our analytical capabilities to go further than we thought we could. Next slide. In addition to partnering with universities, government labs, and private sector labs to run samples using the standard triple quad analysis procedures, which we understand is well out there and being well done by other companies and private sector, the environmental chemistry branch is developing new methods to analyze for PFAS compounds such as PFOA and PFAS on an Orbitrap. And they have been able to get PFNA detection capability down to 5 parts per trillion. This study was quickly pulled together by a team within 3 months because they had the instrument in the lab. They figured they might as well play with it and do a more scoping study. They're going to build off the knowledge that they've developed and try and better the analytical capabilities out there. Future work is forthcoming. The data presented here is just preliminary data they were able to get in their 3-month study to say we need to go forward and actually develop this further. Next slide. Moving on to fate and transport, the ERDC started building physical river models in the early 1930s following the Mississippi flood of 1927. It's a little history note for you. Through the years, the labs have developed world-class physical labs, modeling tools, physical and numerical modeling techniques, and expertise. ERDC leverages combined state-of-the-art hydrodynamic, hydrologic, and groundwater modeling, advanced environmental process modeling, and computing capabilities such as a high-performance computer, suite of high-performance computers, to rapidly deploy tools that enhance DoD's ability to assess and perform water quality, contaminant impacts associated with emerging contaminants such as military unit compounds, explosives, energetics, heavy metals, and we look to incorporate this expertise by looking at emerging water quality concerns such as PFAS compounds. As you can see in the slide, we developed bench scale models that we can adapt to advanced site characterization models and leverage those into further existing models that are out there, and also incorporate aspects of different models into a larger model. Next slide. For instance, I'm working with Dr. Jeff Silva as a lead PI for SERDP project ER 18-1389 to evaluate the air water and Napa water as a reference interfacial absorption within the vadose zone. In general, the initial project objectives were to generate fundamental physiochemical properties data with which to evaluate the significance of air-water interface accumulation as an environmental sink. Investigate the potential for interfacial tension-induced flow and lateral spreading of PFAS in the vadose zone. Incorporate, and this is important, incorporate these results into the HYDRIS model where appropriate for unsaturated flow and transport modeling. The objectives have been slightly modified to adjust to the experimental results that we've currently achieved in the lab, and we're looking forward to publishing this. Next slide. Preliminary results are presented here depicting on the left the calculated retardation value, RF, for Napa water interfacial absorption, where the retardation factors for air water and Napa water interface absorption increase exponentially with increasing carbon number. And on the right in the table, there are some values for the PFCA mass retained at the air-water interface, which illustrates the potential significance of the air-water interface as a source of PFCA retention in the vadose zone. The absorption increased consistently with the ionic strength for PFCA, and also our results showed that numerical simulation may provide a better alternative since PFCA, for compounds like PFCA, since PFCA retention within water unsaturated porous media is shown to depend on a number of interrelated factors and conditions that can complicate the use of retardation factors for predicting rates of transport and field conditions. Basically what this means is we're getting some really cool data and we're seeing some significant results that we didn't anticipate, and we still have a lot to tease out. The results for this work are currently being submitted by Silva et al. And should be out in publication soon. Next slide. So the third aspect that ERDC plans to bring to the table is toxicity, uptake, trophic, transfer, and their effects. ERDC has developed a suite of protocols related to the contaminant toxicity, like I said, uptake, trophic transport, and their effects. Much of the research is done through well-established toxicity studies and protocols that have been conducted in the lab on contaminants such as PCBs, energetic compounds, such as RDX, TNT, and heavy metals. Recently, protocols have been developed to evaluate nanomaterials in the environment also. ERDC is developing research to replicate and evaluate existing PFOA and PFAS toxicity studies to gain a better understanding of the complexity of the PFAS compounds on the environment. Next slide. We work with Daphnia and zebrafish embryos, for example, on toxicity, mode of action, and adverse outcome research. For instance, Daphnia and zebrafish are exposed to different concentrations, mortality and apical effects are evaluated. Samples are used to generate gene expression data and then used to generate a transcription point of departure, together with several other compounds. To assess species sensitivity and for species extrapolation as well, this work is being proposed for PFAS compounds of interest on several sites. We are now developing networks to better understand the species sensitivities and how they interact. Next slide. ERDC has developed novel materials such as quick single pore methods to make chitosan graphene oxide membranes with the potential to be tailored to bind or repel PFAS compounds from passing through a membrane. The treatment approach is to generate a concentrate that approaches zero discharge from a treatment system with a potential to provide a low-cost alternative treatment approach to the concentrate. As you see in the picture on the far right-hand side, that's a membrane that we generated in the lab pretty much overnight, and we're able to replicate this generation and use it to see very little to zero discharge in lab experiments. Next slide. ERDC has a range of expertise in the design, development, and implementation of chemical processes and products to address the most challenging environmental contaminants. Like I said in the beginning, we've cut our teeth on doing a lot of energetic research with RDX TNT. We've done a lot of work with stabilization of metals and detection of metals in the environment. So we have a strong expertise in working with unique compounds, figuring out the best approach and how to tackle them in the environment. ERDC has dedicated facilities with engineering and technical expertise and skill sets to scale prototypes and pilot systems for full demonstration potential. See in the upper left picture, there's an example of a small prototype bench scale apparatus that we've set up. And center picture is more of a prototype field deployable unit that we've designed and built in-house. And the far right picture shows a process control instrumentation unit. It's basically a one-touch system. You can push it, it turns it on, it runs the entire system. Designed that way so we can alleviate some of the operator mode and move on. ERDC is currently working with the Air Force and the Army to build a similar system to demonstrate a mobile treatment system known as the PFAS Effluent Treatment System, or the PETS. A prototype is, as I said, is shown in the middle and will be modified to be deployed to do a field demonstration later this summer or spring. Next slide. Some of the knowledge gaps related to fate and transport that we've identified, and want to link them to others so we can actually come up with a solid solution. In the top picture, you'll see the surface water plus groundwater plus hydrodynamics. We have numerous models and tools to build a transfer component from watershed scale to the pore scale. For example, a number of DoD sites are dealing with PFAS in groundwater where ModFlow available in GMS is a frequent choice for spatially explicit plume hydrogeologic modeling. In the middle, you'll see the fate mechanisms to bench scale to parameterization. ERDC has extensive experience and capability in developing environmental processes, models, and identifying parameters for the environmental process that control chemical fate from the field to the bench scale. Conceptual models and parameterization of environmental process for PFAS compounds are an urgent need that we've identified and want to work on. Table on the bottom, talking about the multimedia site concept, the integrated environmental process, and the fate and transport modeling. The ERDC has the capability to model emerging contaminant fate and transport with several platforms, such as Trex, Geisha, RT3D, to name a few. Trex, for example, can be modified with user-defined process parameters and used to predict contaminant breakthrough times at a downstream target. None of the models currently have PFAS-specific capabilities yet because the environmental processes are an active area of research and investigation in the greater fate and transport research community, such as the SERDP project we're working with Dr. Silva on. Scaling new processes from bench scale experiments to field scale model applications is one of our areas of expertise. Next slide. Knowledge gaps with the mode of action. Mechanisms of action through mechanistic understanding of the toxicity is something that we're interested in and looking into. Also, adverse outcome pathways and the AOP networks and their involvement in how it interacts in the environment is also an interest of ours. Species sensitivity, such as species, sex, and life stages sensitivity is also an interest that we're looking into and how they link into the environment and the toxicology effects. Accurate docking and binding models for the different structures to predict toxicity in specific molecules, such as nuclear receptors, is also an interest that we're looking into. Next slide. So what are the next steps? The next steps are for ERDC to continue our PFAS working group, continue reaching out to researchers at the private and public sector, continue to make our contacts such as ITRC and other intergovernmental agencies, EPA, FDA, USGS, to see how we can fill the knowledge gaps and move forward. ERDC is working on a PFAS meeting. Right now it's looking like it'll happen in March or April timeframe of this year. And we're looking to invite USACE partners at this time. Myself and Dr. David Moore are the point of contacts right now. Our information is below. Next slide. With that, I'd like to say thank you to some of my collaborators, Dr. Chris Griggs, Jared Johnson, Jay Lindsay, Dr. David Moore, and Dr. Jeff Silva for providing information to give you on this presentation and kind of tell you what we're doing. I'd also like to thank the SAME Environmental Committee, Mr. Mike Worminski and Tim Fitzpatrick for their help in pulling this meeting together. Thank you.
Okay, thank you, Andy. That concludes the presentations, and we'd now like to open the call up for about a 15-minute Q&A session. I have a number of chat questions I can start with, and then we can take questions from the call-in audience if there's any more. The first question was directed to Kavitha. Kavitha, can you please respond to this one? The question is, was the high-res method similar to dioxin and furan?
So the high-res mass spec, when we're doing the data filtering, we looked for only the fluorinated chemicals in this one. So the more of the data filtering plays a role in prioritizing what you're looking for. So I think any of the high-res mass specs data would be similar, but it all depends on how you're filtering the data, which parameters you're providing to the instrument to filter the data.
Okay. Another question for Kavitha on slide 32. What was used to determine the difference? In other words, what were the X and Y axes denoting?
Slide 32. Can you please go back on onto 32? Is it the principal component analysis or the high-res mass spec data?
Okay, I think Bill's going back to slide 32.
Do you want to move to the next question while Bill pulls up that slide?
Yeah, and the next question also for Kavitha. Have you seen any evidence that sewers and or septic systems are a source of PFAS in the environment?
So I would think the septic system could be similar to the wastewater treatment plant or the landfill leachate, which is coming out. So the more fingerprint of the septic system could be similar to the looking for the biodegradation products. How about the to better explain that question again, your question was whether it could be the source to the environment. So if there is any leachate coming out of that, that could be definitely, and mixing with any of the groundwater nearby, that could be the source of it.
Okay, and slide 32 is back up.
And could you repeat the question?
Yeah, on slide 32, what was used to determine the difference? In other words, what were the X and Y axes denoting? I believe slide 32 might be an incorrect reference. There's no graph there.
The graph, I believe, is forward. Keep moving. Yeah.
So on this slide, the x-axis is the PFAS analytes. The ones which are ending with A are the carboxylates and the S are the sulfonates, and the 6,2-FTS and 8,2-FTS are either the precursors or the intermediates. And the y-axis is the concentration in milligram per liter for these AFFF.
Okay, we had one other question. I think this one should be directed to Belle or Tim. The question was, will these slides be available and where can they be found?
The slides will be available and they will be posted momentarily once the conclusion of the webinar has happened, and you'll find them on the SAME environmental website. I will send out the certificate for everyone this evening with the link to where the presentations can be found. And also we will be providing a recording. Unfortunately, I can't take out all the mishaps with all the noise that we've been suffering today throughout this webinar, but it will be available on the same SAME environmental website.
Okay, we had additional questions come in from the Army Corps Omaha District for Andy. Does the data indicate that PFAS prefers to be in air as opposed to water, any of the PFAS compounds?
Yeah, I think we're still trying to tease that out right now. What it really looks like is there's going to be a smear zone in the Vados zone that's going to have high concentrations of PFAS. So we're going to have to deal with that somehow. And I think long term, as we clean up sites and we think it's clean, it's going to be kind of a smear effect like we see with chlorinated solvents there. So, you know, long term, I think there's some stuff we have to figure out and how to remediate those or manage those sites.
Okay, very good. That's all of the chat questions that I have. Are there any questions from the audience? If you do have a question, please state your name and which speaker it's intended for. Oh, we have another one here, another chat question. Can fluoride from drinking water treatment contribute to PFAS formation? I think we can address that to all three of the speakers to see if any one of those can provide a response.
Kavita, can you handle that one?
Yeah, so I don't think it can form the CF bond from whatever the fluoride which is out there in the drinking water. These reactions are very complex, and it just doesn't happen that the fluoride could bind with any of the carbon and form a PFAS chemical or form a perfluorinated chemical actually. So I don't think it's possible, and I haven't came across any of the literature reporting such formation.
Okay. Anyone else have a comment from our speakers? I have 2 more questions came in. How does non-aqueous phase liquid NAPLs affect PFAS fate and transport?
This is Andy. Right now we are looking at them separate, and I think that's going to be something we'll look into next to see what the interactions are. Right now we're just trying to tease out, is there an accumulation effect or not? And, you know, the next step of any research is, well, what do you mix, when you mix compounds, what happens? So I think that'll be the next step of the research.
Okay.
Or a good step forward.
Yeah, go ahead, Andy, sorry.
Oh, no, I was going to say, or that's a good step forward, taking what we've learned and move it on and seeing what the interactions will be. And even NAPL or other contaminants that we see in the environment and how they affect PFAS mobility.
Okay, was there a question from the audience there that I talked over?
Yeah, this is T.R. Shepard, the Corps in Kansas City. I noticed on your first slides where you had a value in Vermont of 2 parts per trillion. And then later on, I noticed in another talk that they were getting 2 parts per trillion with standards. Is it really possible to find 2 parts per trillion in natural water?
I can take a stab at that. This is Tim Fitzpatrick with SGS Access Analytical. We are routinely reporting in waters with a 1 liter down to 0.4 parts per trillion with clear differentiation from the blanks.
Okay, any other questions from the audience? Okay, I've had a couple more chat questions come in. Open to the speakers. Has anyone seen any reductive dehalogenation of PFAS, PFOA under strongly anaerobic conditions? Kavitha, Andy,
Yeah,
any input?
Yeah, this is Andy. The research that we've done, I don't think we've seen that, and I could be speaking out of turn, but I know that there's some active research proposals that are going in to look specifically at that and see what we can do or what's out there and what's available in the biota that can do stuff. So that's a great question, and I don't know the answer to it, unfortunately.
Okay, we have another chat question addressed to Kavitha. How many non-target PFAS compounds are you attempting to identify?
So when we did this non-targeted analysis, I got almost like 20,000 hits from each sample, actually. So after a lot of data filtering, I have cut them down to 250 in the environmental samples, and in AFFF samples, I still had around 500 analytes were there, non-targeted chemicals were there. But these list also include some of the known chemicals, and whatever the library I had, I was able to sort out the known chemicals out from those non-targeted chemicals, analytes.
Okay. I have no other chat questions. Any other questions from the audience? Well, I've had another chat question come in. In terms of fate and transport, are there any current studies of PFAS, PFOA dust from soil and sediment from contaminated sites, i.e. fire training area, and its associated inhalation risk?
Yeah, this is Andy Martin. The dust isn't really in our core mission, unfortunately, but we did identify that as an issue in terms of burning and fate and transport in the atmosphere. And that, that's a great topic that someone needs to look into, I think, from the training areas. And that would really close the loop on some of the fate and transport aspects and what's happening with PFOA, PFAS in the environment.
Okay, Ginny Yingling, is this something that is on ITRC's radar and your team's radar as well?
This is Tim Fitzpatrick. I'll just say that in a related topic, ATSDR is sponsoring their new national PFAS study, which will be starting here in the next couple of months, and they will be looking at household dust as a potential source of PFAS exposure. And they're looking at sampling dust from possibly several hundred different houses across the country as, again, part of their national PFAS study. Speaking about dust.
Okay, thank you, Tim.
This is Ginny. Sorry, I reached for my mute button and hit my headset button instead. So sorry about that. It's not something on our radar screen in terms of for ITRC in terms of anything that we've seen yet. It was certainly a question on our conceptual site model for the AFFF sites. We have a big question mark about airborne emissions from AFFF sites. And so I think it definitely is a data gap that's out there. I think a lot of people have the same question about municipal incinerators and whether or not burning of consumer products containing PFAS is contributing to emissions as well, both either dust or volatile.
Okay, any other questions for our speakers? I don't have any more chat questions. Okay, with that said, I'd like to extend a warm thank you to our speakers and the attendees. And on behalf of the Society of American Military Engineers and the Environmental Committee, we appreciate everyone's participation and hope this webinar has been useful. This concludes the webinar. You may now disconnect and have a wonderful day.